Hi everyone, this is Rick, and this week we are doing the effect of load on solar panel output. Now load is very important in the design of a solar panel, and I want you to consider that the load in a circuit is something you design around, and you want to design a circuit with a certain load in mind. It helps you to maximize your power output. I'm going to read some of this aloud to you, and then we'll go through some of it. Some of it I've already done. It reads, given that there is a seemingly endless supply of energy available from the sun, solar panels are becoming increasingly common. Solar panels, which are most often made out of silicon, a semiconductor, have the ability to convert light energy into electrical energy, which you already knew. Here's something you may not know. In this experiment, you will test a solar panel to determine how load, in this case a resistor, a lot of times it's like a heater or something you're trying to do with it, maybe charge a battery, affects its power output. You will create a potential current curve known as the IV curve. IV is because I is the symbol for current and V is the symbol for potential. Current is measured in amperes or amps, and potential is measured in volts. Here's figure 1, for example, and it says Vmax, Imax, and it says ISC, Pmax, VOC. The reason it says this and these little lines are drawn here, which isn't clear at all in reading this, is because if you were to take the slope of this curve, this is the point of inflection, and that's some mathematical thing we're thinking about, but don't worry about it too much. And this here, it says, oh, there's the two things we're concerned with. There's the VOC, which is the open circuit potential, which is the voltage when there's no current, and then the current when there's no voltage, which is this point and that point, are the two things that go into this that help us to frame some of our math, because the Pmax has to be a point in between those, the most power that we can get out of the system. And it's always where that curve, if you were to do the second derivative of this curve, you would make a little inflection point. You would see it. Anyway, I get ahead of myself. Two useful pieces of information you can learn from an IV curve are the open circuit voltage and the short circuit current. VOC is the voltage when the resistance is infinite. Well, resistance is infinite when you don't have any current, right? When there's no load connected to the system and the current is 0 milliamps. And the ISC is the short circuit current, is the current when the resistance is 0 and the voltage is 0. These quantities appear as the horizontal and vertical intercepts on an IV curve. That intercept means where it crosses this line right here. That's the line, in this line. So we are going to do that. So I've done all the setup and the zeroing out here. And so we've done these parts. And I am going to switch cameras in a moment, and I will continue. All right, so we're going to go ahead and get the open circuit potential and the ISC, short circuit current. So no load at all, hooked up to the device. I get 2.28 volts. So I'm going to write, or 2.25 volts. I'm going to write that here in the data table. So 2.25 volts. Then I'm going to short circuit the current, and I'm going to shunt it. So I'm going to take this and literally take the load offline. There should be no potential at all. And I get 60.3 milliamps. So I'm going to write down 60.3 milliamps. Then I'm going to take the curve of my data. So I'm going to hook this guy up to here, this guy up to here. Tighten everything down, and then what I'm going to do is I'm going to start a graph, which you'll see some of my other ones here I started before, practicing to show you this. Whoops. I am going to plot them on a time scale. So what I want to do first is take these, put them on both on time, and there's going to be potential on the top, so you can see what happens over 30 seconds. I got to get to 60 milliamps and drop from 2 volts in that much time. And I'm going to go ahead and collect data for 30 seconds, and I will slowly increase this, and you'll see what happens over time. So here we go. I'm going to try not to get to too quickly, and this is going to take a dive. We got to get to 60. milliamps. Let's see here. There we go. I'm just going to take this thing off the cliff there. Let it just sort of drop down. That'll give you enough resolution in your graph, and it will stop in 2 seconds. There, stopped. That is a graph of the time versus current and potential. I'm going to switch cameras. Now, this is both of them versus time, and I really want you to see the potential versus the current, which will be that IV curve that you have before. So I'm going to just take this one and change this to the potential. And this will be the, this will be the current. This will be the potential, and it should drop off and look more familiar to you. Not only that, if you want to label your, oops, I'm going to squish it down a little, and I'm going to make this longer so it looks more like the graph you saw earlier. Remember that 2.19, that open circuit VOC was right here. Like we started that right, well, it's actually right here exactly. So this is that line. And then the 60 point whatever milliamps one was this line right here. So this is the ISC part. And it says in the graph here, it says to print a graph of the current versus potential, label VOC and IC. That's what we do. Identify the point of graph would be the highest power output. Well, that, my friends, is going to be right about here. And wants to do next is we want the resistance to get the load on the system. What is the load at the maximum power point? Sketch a graph of the power versus load resistance. Well, we don't really have to sketch it because we are good at what we do. We can just turn this to resistance, and this can be power, which is the current times the potential. And it should be, what happened here? Power milliwatt, current time potential. That went crazy. That is not what that's supposed to look like at all. Let me explore this for a second. Okay, there was one data point before that was out that made it sort of take it in a bad way. So let's try this again. We're going to go with resistance times power. That's more like it. So we have a maximum right here. The maximum is 109 milliwatts, and whoops, let's turn off the voltage. There we go. It's 109 milliwatts and 36 ohms. So you might want to take a screenshot of this little guy here. So that's what we want to see. I'm going to do one more data point where I'm going to spend a little more time around 36 ohms so you can see a little better. And so I'm going to do, I'm going to get the resistance, and I'm going to record it here so we can see what this looks like. And I'm going to spend a little more time right about there so you have a little more resolution in it. And then I'll just show you. Here we go. Didn't want to get up to it too quickly. So this one should have a better, we should be able to see it more easily. There. Now that's what I was trying to do. I was trying to zoom in on a little better. This one's, they're about the same. Anything about that's fine. 111 milliwatts and 35.2 ohms. So this is how you want to design your system. If you design your system to run with this much resistance in it, you'll get the most power out of your system, most power delivery, because your system is tuned for that. So let's take a look here what we're answering. It reads, what is the load resistance at the maximum power input? Let's put 35.2 ohms, and it's this is that graph right here. How does power, actually let me pause this for just a second so you can take a screenshot in case you want to. Then sketch a graph. In many cases, electrical load on a circuit is a device such as a motor or a heater, of course. Well, why else are you doing with electricity? What are you doing, right? These devices often come in varying sizes, different power ratings. Now, obviously, you can see if the resistance was higher or lower, you would get on either side of this, higher or lower, you would get different amounts of power. Less power out, you want most power, right? So that's what you do. That helps you determine that. You don't have to do the extension part. And that is it. That's the whole lab for this week. I hope you enjoyed it. Take care. Bye-bye.